This video is about associativity, or the associative property of matrix multiplication. The associative property has to do with these triple products, and it is one aspect in which matrix multiplication is similar to multiplication of ordinary numbers. So let me ask you a question about ordinary numbers first. What is 13 times 25 times 4? And the answer is, of course, 1300. And I think all of you got that answer in the exact same way, by multiplying 25 by 4 first, which gives you 100, and then multiplying the result by 13, and 13 times 100 is, of course, 1300. So that was the smart way to carry out this triple product. Let me indicate with parentheses what you did. By evaluating this product first, you effectively place parentheses this way. We usually use parentheses to indicate precedence of operators. And in this case, the precedence was given to this multiplication. This notation indicates that you have to do this product first and then multiply the result by 13. And why was it valid to do that? Well, that's because multiplication of ordinary numbers is associative. Associativity means just that when you have a triple product, it doesn't matter whether you do this product first and then multiply the result by 4, or do this product first and then multiply it by 13. In both cases, you would get the same result, so you should choose the version that's easier to carry out. And that's, of course, doing this multiplication first. So if we wanted to capture this associative rule with letters, as we usually do in algebra, we would write that AB in parentheses times C, meaning the product AB is done first, and then the result is multiplied by C, would yield the same value as A multiplied by the product BC. And here, the parentheses indicate that the second product is to be done first, and then the result is to be multiplied by A, and the equality sign means that in both cases, we get the same thing. Well, if we get the same thing in both cases, then we might as well write the whole thing without any parentheses, unless we specifically want to indicate our precedence. So we can write it without any parentheses, meaning that whether you do this or this, the result will be the same, and it's up to the reader or the viewer to figure out the best order to carry out this multiplication. But the ultimate answer certainly doesn't depend on the order of the operations. That's associativity. Now, the matrix product is associative as well. Let's first make sure that all of the dimensions are compatible. Here we have a 2 by 3 matrix multiplied by a 3 by 2 matrix multiplied by a 2 by 4 matrix. So the inner dimensions match here and the inner dimensions match here. So all of these products are compatible. And also, whether we do this product first or this product first, the intermediate expressions will also be compatible. If we did this product first, we would end up with a 2 by 2 matrix, which would then multiply a 2 by 4 matrix. That's compatible, and the result would be 2 by 4. If we did it in this order, the intermediate result would be 3 by 4, and that's being multiplied on the left by a matrix that's 2 by 3. So once again, compatible dimensions, and once again, the answer is 2 by 4. So this works out perfectly. All of the intermediate expressions are compatible as well, and in both cases, the answer would be a 2 by 4 matrix. And will it be the same 2 by 4 matrix in both cases? And the answer is yes. And I will actually illustrate it on the computer. So yes, the matrix product is associative, and it is one important way in which matrix multiplication is similar to multiplication of ordinary numbers. 2 notes. Number 1, I don't think it is at all obvious why matrix multiplication is associative. So you can do one of several things. You can take my word for it and move on, or you can consider enough of these triple product examples, and each time calculating the triple product in 2 different ways and making sure that you get the same answer, and that may convince you that you would get the same answer in all cases. Or you could take this 2 by 3, 3 by 2, 2 by 4 example and replace numbers with letters and calculate the product in 2 different ways with letters, and then compare the answers and make sure they're the same, And I think you'll see enough patterns in that result that you will understand why it happens for all possible dimensions of matrices. Or you can watch a video that I'll record that actually includes the proof of the associative property of matrix multiplication. So whichever choice you make is perfectly fine with me. And number two, even though it doesn't matter the order in which you carry out the multiplications, sometimes one way is smarter than the other, as it was in the case of these three numbers. So consider this example. Suppose you have to multiply, I'll just sketch it out, a 4 by 4 matrix by another 4 by 4 matrix. Let's say by another 4 by 4 matrix. All of these are compatible, of course. And then finally by a 4 by 1 matrix. What's the smart, regardless of the numbers in these matrices, what is the smart order to carry out these operations? Is it like this? Or is it like, let me use different colored chalk, like this? So in other words, to do this product first, followed by this product, and then finally followed by this product. Well, the second choice will result in many fewer operations. You can calculate the number of operations that it takes to multiply two 4 by 4 matrices. But there are 16 numbers here, 16 numbers here, and 16 numbers in the answer. And then you will multiply it by another 4 by 4 number, so it's another 16 mixing with 16, and the result is once again 16 numbers, and so forth. If you do it in the opposite order, you would multiply this matrix by this one, the answer will be 4 by 1. So it's actually 1/4 of the work. And then this product times this, what's now a vector, is again once again 1/4 of the work. And then one more time, 1/4 of the work. So the associative property gives you a choice. That's the beauty of the associative property. And you should always make the smart choice. So that's associativity. Let us illustrate associativity by taking advantage of the built-in matrix algebra capability of the system. We will evaluate this triple product in two ways. First, in this way, and second, in this way. And we're hoping that the answer will be the same, whether we do this multiplication first or whether we do this multiplication first. Let's do it the first way first. Evaluating this matrix product will result in a 2 by 2 matrix, this one. And now what's left to do is to multiply this matrix by the remaining 2 by 4 matrix. And the result is this. Okay, so that's our final answer. And we'd like to see whether we would get the same answer by evaluating the triple product in the opposite order. Evaluating this product will yield a 3 by 4 matrix, this one. And what's left to do is to multiply, keeping the order of the matrices, by this 2 by 3 matrix. So this 2 by 3 matrix by this 3 by 4 matrix will result in the 2 by 4 matrix, this one. And lo and behold, it's the exact same matrix as we obtained before. So associativity holds. And I think it's very interesting to note that the intermediate matrices could not have been any more different. Well, that's what associativity really means. That even though the intermediate results are completely different, because they come from the same triple product of the matrices, the only difference being the order of the operations, the result will be the same. That's associativity. And because we have the associative property, we can write the triple product without any parentheses, and the system will evaluate this triple product in any way it chooses. It will probably choose the way that results in the fewer number of operations, the result being the same 2 by 4 matrix. So there we go. That's our illustration of associativity, or the associative property of matrix multiplication. All right, there you go. Next we'll talk about commutativity, or the commutative property of matrix multiplication. And it'll be one aspect in which it's not like multiplication of ordinary numbers.